PFD calculation. I'm reading two screens at once. Today we're going to talk about a surprising number of key variables needed for PFD calculation, and I will show you an example of why these are so important and give you some guidance and show you a few formulas to calculate PFD average. My name is Bill Goble. I work for a company called Exida. Exida is a global safety knowledge company and certification body. We're composed of a number of different people from very different organizations. We are familiar with new product development, safety certification, and systems level design. All of our work, although there are many different things that we do, all of our work is very focused on automation equipment, availability, safety, and cyber security. I'm happy to say that Exida is heavily technically oriented. We do a lot of research, and we publish most of our research as a publicly available book, available on Exida.com or Amazon.com. Many of our books are available right on Amazon. You've got a little background on myself and the company. Let me talk about safety instrumented function verification. Many of you realize that IEC 61511, the functional safety standard for the process industries, is based on IEC 61508. And there are two fundamental principles. If I take all the requirements from hundreds of requirements, they boil down to two fundamental concepts. Number one, you need a detailed engineering process that you follow to help reduce design mistakes, what the standard calls systematic faults. Now, it's more than design mistakes. It's mistakes through the entire safety life cycle, including mistakes in requirements, mistakes in architecture design, mistakes in detail design, mistakes in documentation, mistakes in maintenance procedures. All of these things are important in the safety life cycle. And the 61508 standard and the 61511 standard have very specific requirements that we must meet to protect ourselves against design mistakes. Why? Design mistakes can cause a system to be unsafe, of course. The other fundamental concept is a probabilistic performance-based system design. What that means is there are no rules. There is no cookbook to design to a given sill level. You must do this, this, and this. You must have a double block and bleed valve. You must have 14 temperature transmitters. No, there's none of that. What it does say is that you are responsible for coming up with a design, and then you are responsible to verify that that design meets requirements. And that's what we're going to be talking about today. In the safety life cycle, we verify that any given design meets requirements. We do that by checking three design barriers. Number one, systematic capability. And in the world of 61511, that can be done with either typically choosing a certified part with systematic capability to the given sill level, or by doing a prior use justification to the given sill level. Barrier number two, we calculate a PFH if it's called a high demand, or a PFD average in a low demand, typically process industry application. Barrier number three, we must meet minimum architecture constraints. And there are many different tables to use. There's a couple different tables in 61511. There's basically three different ways to do it in 61508. All three of these barriers must be met, and if the three barriers tell us we meet a given SIL level as a requirement, design is good. If a design does not meet one of the barriers, worst case SIL level wins. Now today, we're going to be focusing on barrier number 2, the PFDavg calculation, and the low demand situation which is prevalent in the process industries. You probably all know about SIL levels, and SIL levels are defined in 61508 as 1, 2, 3, or 4. The highest safety is achieved in level 4. The lowest safety is safety integrity level number 1. And there is a table that says a PFDavg for a given set of equipment must meet a number within a range, order of magnitude range, as you can see on this chart. So what we're going to be talking about today is how do we calculate this number that gives us a safety integrity level based on this chart. Let's say we're talking about SIL 2. For a set of equipment, not an individual piece of equipment, but the entire set of equipment that comprises a safety function, you must meet a number between 10 to the minus 2 and 10 to the minus 3. So let's see if we can do that in an example, and let's see what all the things we should consider. As a result of Exeter's research, primarily into literally hundreds of sets of field failure data, we have seen a number of things significantly impact a PFDavg. Now look at this list of 9 items. I'm sure you've seen some of them before if you've done any PFDavg calculations, but many of you perhaps have not seen some of these items. In fact, I didn't know about some of these items until we discovered them by studying field failure records and proof test records. It's interesting what all this data actually shows us. Look at it. We need, number 1, failure rates. Number 2, we have to account for redundancy of devices. Well, of course. We have to account for proof testing and proof test intervals. We have to account for mean time to restore if we're out repairing a piece of equipment. We have to account for proof test effectiveness. How good is the proof test? We have to account for a variable called mission time. How long are we going to run the equipment? We have to account for how we do proof testing. Let me ask you to think about this for a minute. I'll be covering it again, but what happens if we put a safety function into bypass during a proof test? If that happens, proof test duration is a significant variable in the PFD calculation. Yeah, probably never thought about that. It's certainly not a variable in the 61508 simplified equations. And lastly, operational maintenance and capability, which is something Exeter is modeling only in the last few years. 9 variables. Oh, by the way, anytime you have a question or a comment, go right ahead and type them in at the Q&A tab at the top of your screen. I'll be happy to stop and answer those questions. Any comments like, for example, I never heard of proof test duration. Well, I understand that. There are many courses and many educational opportunities that simply don't present all of that information. Let's go back to the fundamental basics from the early days of reliability engineering. A function was defined and named reliability, and for a constant failure rate and a number of simplifications, the reliability function is e to the minus lambda t, where lambda is the failure rate and t is the mission time. It's a time interval. unreliability is 1 minus e to the minus lambda t. We're going to start with that basic fundamental definition. Now, there is a very useful approximation that makes it a simple linear equation, and you can look at that and you can get an idea that there is a series expansion, and if we approximate that with e to the x is approximately equal to 1 plus x, we can substitute the minus lambda t notation, and you'll discover that the unreliability function is approximately equal to lambda t. Failure rate times mission time. All right. Now, an alternative notation is probability of failure, PF, and that's where our PFD comes from. You can look at, in fact, the approximation versus the real function, and you can see that the approximation is actually somewhat pessimistic, but in fact, at a very low level, a small probability of failure, especially when the probability of failure is less than 0.1, the approximation is relatively accurate. Most of the time I've calculated a number like 3 or 4%, and that is just fine for safety, because even SIL 1, the worst number on the entire chart, was 0.1. So we are going to be working entirely in this range, circled by or boxed by the red box, and so we're going to be using the approximations to make things simpler, and that's exactly what the various committees have chosen to do. The problem is, of course, they didn't recognize all the variables involved. Now we have a problem, or we have a challenge, let's say. In the process industries, we can do proof testing. We're not on an airplane in the middle of the air where we can't test the flight controls. We're not on a space mission where we cannot possibly test if the booster rockets work or not. We are in a process control environment where, in a safety instrumented system, where we can actually test if a safety function is working or not. So let me ask you the question, how in the world do we account for that? And the answer is, ask yourself the question, when we do a proof test, and let's assume for the moment it's a perfect proof test, idealistic and unrealistic, but assume that for the moment. We know there is no failure, so what probability do we assign? And the answer is 0. If we know that it doesn't fail, we know that the probability of failure is 0, and this is how we model the probability of an ideal proof test. Hope that makes sense. If you want to read more about it, don't hesitate to go to the book Control System Safety Evaluation and Reliability, which describes the entire derivation of all of this in great detail. It's available from isa.org or exida.com. So we understand how to model a proof test, and we end up with this probability line that kind of looks like a sawtooth. Well, why in the world do we take the average of that line? Well, in low demand, a dangerous condition occurs infrequently, and it's considered an independent event. Equally likely at all moments in time, ideally. Therefore, it could come when the probability is very low, or it could come at the moment when the probability is high, or anywhere in between. Therefore, since it can come at any time, and it's equally likely at any time, it's completely legitimate to take an average of this function. So the term PFAvg was defined as an average of this probability over a long interval of time called the mission time. Hope that makes sense. I know I had a hard time accepting that when I first heard this explanation. Got to use PFD peak. I remember arguing that in one of the early committee meetings, but they said, no, the reason we justify this is simple. Demands are independent events, equally likely in time, and can come at any moment, and therefore the number we want is the average. Yep, okay, I was convinced. We can do an approximation for an ideal PF average. Remember, if our probability of failure approximation is lambda t, where t is the mission time, now we define the quote, time interval of interest as the test interval. PF average equals lambda times ti divided by 2. And you can almost see that by just looking at this. You can see it graphically by looking at this triangle. I kind of remember something about this from high school geometry. And I'm not going to go through the derivation of the math right now. You can look that up in the book. But there is an equation for approximate PF average, lambda, the failure rate, times a test interval, divided by 2. Now, all we have to do to convert that to dangerous PFD is only look at the dangerous failure rate, not the total failure rate. So the term PFD is probability of failure on demand or probability of failing dangerously. Fortunately, both of those end up with the same acronym. And the average is lambda d times the test interval divided by 2. Now, many of you will recognize that. It's a common equation published in many textbooks and introductory material. It is, of course, very idealistic and unrealistic, as is the entire point of this webinar today. But it's a great place to get started. Now, what variables have we covered so far? We've covered number 1. We want the dangerous failure rates. And we've covered number 3, the PFD, or the proof test intervals, the variable TI. Makes sense so far? Okay, so far we have 2 variables for PFD average. Okay, what about the other 7? All right, be patient, we'll get there. How do we account for automatic diagnostics in a product? Imagine that you have a high-class, safety-rated pressure transmitter. And this pressure transmitter has excellent automatic self-diagnostics. And the pressure transmitter sends the current level to an out-of-range condition. And the logic solver is programmed to recognize 20.8 or whatever the number is out of, I think it's more like 21 milliamps as a detected failure. Well, the logic solver or the logic solver programmer or the system designer can choose to either make that a trip, or the logic solver designer, in most cases in the process industries, enunciates that failure so the repair team can go out and fix or replace the transmitter rapidly. And therefore, we take the lambda d and divide it up into 2 subcategories. Lambda dd, dangerous detected, and lambda du, dangerous undetected. Now, the number we were talking about in our simple equation is dangerous undetected, because nobody detects it until we go out to do a perfect proof test. But what about the DDs? Let's assume we didn't vote to trip. So if the failure is detected by an automatic diagnostics, and the failure is enunciated to operations personnel, and a repair is dispatched quickly so that the average repair time is maintained, I know that's a lot of conditions, but that's exactly what can happen, then the dangerous detected failure only contributes to the PFD for a small duration of time called mean time to restore, MTTR. There's no average on that. it's simply lambda d times MTTR. Every time it fails, we fix it. As long as we maintain the average repair time, this portion of that equation is valid. Okay, what did we just... Now, what about redundancy, I mean? Many people will take these simplified equations and calculate probabilities, put them into fault trees, where we add up the probabilities if an OR gate is involved, or we multiply the probabilities if an AND gate is involved. And if we do that and use these simplified equations, and this is exactly what's done, for example, in Part 6, the informative portion of 61508, as illustrative examples. The problem with it, of course, is you have to be very careful about doing averaging before the logic, because you get a very different answer than averaging after logic. And that's explained in great detail in the book. We don't have time to do that today. But the bottom line is, if you have a valid method of accounting for redundancy, and you properly account for all the variables, including common cause failures, we account for those 3 variables, and if we account for mean time to restore, now we have covered 4 of the 9 variables. And our equations are not too complicated yet. Don't worry, they're getting there. What happens in a real proof test? It can clearly and definitively be proven via example that no real proof test is perfect. I have many examples of failures in products that cannot be detected by fundamentally simple functional proof testing. Although a lot of people think, hey, if it works, it works. All I have to do is, for example, run that pressure up, make sure the valve attempts to close. You just won't believe how crude some of the proof tests are. One of the most obvious examples is if you do a proof test by putting a block on a valve, checking to see if the valve attempts to move, you have no idea if the seat actually seals or not. So that's far from a perfect proof test. I only picked that example because it's so obvious. What happens if you have an imperfect proof test? Well, instead of taking the probability to 0 during each proof test, we take it to some finite value above 0. And the probability grows and grows as a function of the number of proof test cycles. And the number of proof test cycles in this case is totally equivalent to mission time. You can see, if you look at the black line called PFAvg, that's the average for one cycle. That's the number you get with the simplified equation, the one we just showed you. Even one that accounts for DD and MTTR. What we really need is an equation that gives us the red dotted line. Because over a mission time, the probability of failure keeps growing every test period. Oh boy, is that a big deal? Yes. Countless examples show that it'll change. That variable alone can change a result by one whole sill level, as you can see on this slide. Now, if we go back to a very simplified approximation, and we have an estimate of proof test effectiveness, the coverage of a proof test, the formula for the initial part of the equation, the du part, simply gets divided into the part that's detected during a proof test, this first term, and the part that's not detected during a proof test, which is the second term. I did want to simplify this for you and give you one variable at a time. That's how you account for proof test. That gives you a good average over a given mission time. So we've covered now the dangerous failure rates, the detected and the undetected. We've shown you how to deal with redundancy of devices, proof test intervals, mean time to restore, proof test effectiveness, and mission time. Those last two variables, 5 and 6, come in together when you account for imperfect proof testing. Now, remember that question I asked you at the beginning. What happens when you put a safety function on bypass? What is your answer? Think about it. If you put a safety function on bypass, that means it will not respond to a demand. And of course, the reason we do that is we often run a proof test by creating an artificial demand, and we don't want a false trip. That makes sense? False trips are bad news. Although not everybody recognizes that, they really are. What happens during the proof test? The probability of failure on demand during that brief period equals 1. So we have a function that's approximated by a linear slope and a line that goes up to 1 for the duration of the proof test, then back to 0 if we have a perfect proof test. Think about that for a minute. Many people using simplified equations decrease the proof test interval. I've seen them as short as 1 month. If, for example, it takes you 8 or perhaps even 24 hours to run a proof test, that's a really long, 24 is a long time to leave a safety function in bypass. So let's say 4 hours is a realistic time to leave a safety function in bypass. But 4 hours during a 1 month period, that is a significant limitation. Think about it. Go do the calculation yourself real quick. How do we deal with that? Well, the time spent in bypass occurs once every proof test interval. And therefore, the PFD average due to this reality is a new term, MTTR, divided by test interval. Now, if mean time to restore isn't the same as bypass time, then you must put in your actual bypass time. Most people use the same number for both. Make sense? We're getting a lot of terms. I haven't put them all together yet into one equation, and I wasn't going to bother because it kind of gets so complicated it doesn't make sense unless you really stare at it, and we don't have time for that. But I did want to show you that we've absolutely accounted for bypassing during proof testing, which requires that we account for proof test duration. Yeah. None of this is, of course, in the examples in 61508 Part 6 or many of the simplified equations even used by some of the commercial tools. But I hope it all makes sense to you, and we've covered 8 of the 9 variables. What about this operational maintenance capability? I think I can just hear your voice. I can hear your thought. I've never heard of that before. And in fact, it's only 3 or 4 years ago where our research indicated it was a significant variable based on proof test results. But I will tell you that the thought started in the late 1980s when a group of people who are now with Exeter were doing field failure return studies at Moore Products Company. We found that the return rate for the exact same model number, same design strength. In fact, in this case, it was even the same corporate client with allegedly the same maintenance procedures. We found a difference of 4x in the failure rate, or the number of returns. Why? That was such a mystery, it was investigated. Now, some of the failures were due to some very systematic problems where untrained people were hurting or damaging the equipment during the proof test process, which can happen too. That's why proof tests aren't perfect. That's another reason why proof tests are not perfect. Since the 1980s, several other field failure studies from a number of different sources, primarily end users, process industries, nuclear and power, have indicated there is a fundamental difference in failure rates of the exact same product from site to site. Typically, the ratio is averaging about 2x. Now, what am I talking about? Well, random failures can be divided into two categories. We have, of course, failure rates attributable to a product, and those include a manufacturing defect, really unexpected stress events that actually exceed the strength of the product, and some perhaps random support equipment failures, which all can be considered or could be considered product-related failures since they deal directly with the strength of a given design. But some things, including random maintenance errors, are site-specific and have everything to do with what some people call the safety culture. I have several examples of equipment that was actually damaged during testing and calibration. Actually, a word would be more like dozens, because we've collected information from literally hundreds of different sources, and we have 150 billion unit operating hours. I truly believe Exeter has more process industry failure rate data than anyone in the world. We see these things when we study this data. And of course, some unexpected stress events that are far greater than the published specifications. So it's obvious that people make maintenance errors, and some places don't make very many, and some sites make a lot more of them. How do we deal with that? Well, we also discovered in a paper actually published in the Reliability and Maintainability Symposiums 3 years ago that probability of successful repair is impacted and varies significantly from site to site. Probability of successful proof test varies from site to site. And probability of doing a proof test on schedule is highly variable from site to site. So at Exeter, we created a model of this based on maintenance, based on operational capability levels, and we've defined that and put it into our tool, the Excellentia tool. And we actually vary the probability of successful repair, probability of successful proof test, and the probability of doing the proof test on schedule, considering these somewhat stochastic variables, and take this into account during the proof test calculation. We have a whole paper on that exact subject. We published one at the Reliability and Maintainability Symposium, and another one is about to be published at an AICHE Process Safety Symposium. So we can get you a copy of those papers if you're interested in the model behind all of this. It is published. We do make everything we do public. And sometimes it takes us a little while because we're kind of busy. That's okay. Operational maintenance capability is impacted by all these things. Well, how can that impact PFDavg very much? All the variables listed, all 9 variables listed, are important. As an example, consider a high-level protection safety function. The proposed design let's say it has a SIL2 target. And we've chosen a single SIL3 capable level transmitter, a SIL3 certified safety logic solver, and a single remote actuated valve consisting of a certified solenoid valve, a certified Scotch yoke actuator, and a certified ball valve. Why pick all that certified stuff? We don't have to worry about barrier number one, systematic capability. We're going to use Excellentia, the Exida SIL verification tool. But we're going to enter variables that are very idealistic. In other words, unrealistic. Pick a mission time of 5 years. We'll pick a proof test interval of 1 year for the sensor and the field elements, and 5 years for the logic solver, because really logic solvers have really good automatic diagnostics. We're going to assume a proof test coverage of 100%, which is, of course, ideal and unrealistic, but commonly used and hidden, so people don't even know they're assuming that even in some commercially available SIL verification tools. And we'll assume the process is done, or the proof test is done with the process offline. If the process is not online, there can't be a PFD because there can't be a demand. So that eliminates the whole worrying about bypassing, which is exactly what you do when you use a simplified equation, even the 61508 equations. Okay, I got a question. Thanks. I love questions. Can you clarify what's meant by mission time? Yes, thank you. Good question. Of course, originally it was defined by the reliability engineers as the amount of time we do the calculation. And of course, originally it was defined like the amount of hours in a flight across the Atlantic, because they were worried about World War II airplanes. Really. Now it is a function of how many test intervals you want to perform a calculation. Now, how do you know how many test intervals you want to perform a calculation? And that's basically a time period that you run a process before there's a major shutdown and overhaul. So it could be 5 years. Lately, I'm hearing people talk about 10, 15, or even 20 years. The amount of time you run a set of process equipment before a major shutdown, rebuild, and overhaul. I think that's a good way to do it. Of course, a simple explanation is it's the amount of time you want to run a calculation. Now, in this example I picked, thank you very much for the question. Please ask more. And you can ask that one again if my answer is not good enough. Maybe a mission time of 5 years is realistic. I think many processes are running for longer periods. And of course, just a shutdown without a refurbishment is not the end of a mission time. I've seen many situations where there was a shutdown, there was a good set of proof testing done during the shutdown, but there was no major overhaul. So a mission time is the amount of time you run a process before shutdown and major overhaul. So that all the equipment is replaced or rebuilt, as all the safety function equipment is replaced or rebuilt as new. What do you think the PFD average will be for this example? We're going to meet SIL3, SIL2, SIL1. I should put a poll in so you can think about it ahead of time. Oh, I see more questions. This is great. Could you please explain the 1H and the 2H routes? Well, actually, we have an entire web seminar on that subject, which is recorded and will be coming up again. But basically, in the new version of 61508, 2010 version, 1H gives you a set of architecture constraint charts based on a variable called safe failure fraction, which is calculated in the Excellentia tool if you choose 1H. 2H is based on if you have credible and sufficient field failure data so that you have complete confidence in the failure rate information, you can use route 2H, and the architecture constraint charts are different and simpler, much like the prior use architecture, in fact, exactly like the prior use architecture constraint charts from 61508. But I have a whole web seminar on that. I love the questions. Thank you. What criteria can be used to select a more realistic proof test coverage? Oh, good. I can see we've really got you thinking here today. Great. At Exeter, we do failure mode effect and diagnostic analysis, and we have a whole web seminar on that subject. But when we're finished evaluating the automatic diagnostics, then we evaluate the effectiveness of one or more proof tests. So in many FMEDA reports, Exeter will publish an example proof test and give you a relatively precise prediction of proof test coverage. We've also estimated rough proof test coverages and published them in several of our books. I know that our final element book has a full table of proof test coverages, and the Blue ISA book has a table of proof test coverages as a function of instrument types, primarily solenoids, actuators, and various types of valves. So, and there is a whole web seminar on that, but that's just the short answer. Another one. You will guess. Good, I got a guess. I will guess a high SIL 1 for your example or a low SIL 2. Well, let's find out. And another one. Thank you all so much. If a transmitter and sensor is pulled out, overhauled, calibrated, and put back to place once a year, should this be considered a mission time or a proof test? A transmitter and the sensing device, like a remote seal, or in the case of a temperature transmitter, the thermocouple and the well. Overhauled, rebuilt. I assume you either put in new components or completely restore the old components. Well, that for that particular component, I could see taking the calibration time to 0. That's a lot of work, but I could see using a low mission time if that's what you do every year. I don't know that I've seen that in practice, but I could use a mission time for that. You could also use it as a proof test. Now, there's also an equivalent. I could call that a proof test with a very high coverage factor, like 99 or even in this case 100%. Good question. Another question, how do you determine or calculate the effectiveness of proof test? Oh, good. Well, that's the same, similar question as before. At Exeter, we use an FMEDA for any particular valve. Now we've done 200 or 300 of these, and we've seen very similar proof test coverages as a function of proof test type and as a function of the application environment. We have published many of these numbers in our books, and you will find them in our Safety Equipment Reliability Handbook. I'm not sure how you could do it without a detailed analysis, other than looking it up and applying general conservative numbers. High SIL 2, or high SIL 1 or low SIL 2. What we got, good guess. In this unrealistic example, I got a PFD average of 6.82, e to the minus 3, which meets SIL 2. Now, if you can read these tiny little numbers, you can see that the architecture constraints meet SIL 2, the systematic capability met SIL 2, the PFD average met SIL 2, So the design meets SIL 2. I'm a little confused. Why would the PFD's architecture constraints? Let's look. Architecture constraints. Logic solver with SIL 3, a single sensor, and a single remote actuated valve met SIL 2. Systematic capability, we were limited by the sensor, which met only SIL 2. The logic solver and the remote actuated valve met SIL 3. All right, well, you can see in this tool the details of the calculation, where the problems are. Interestingly enough, look at this blue area over here in the pie chart. The major contribution to PFDavg is final element. The tool also calculates a very important variable, your mean time to fail spuriously, and we like to see pretty high numbers. Overall, this has a pretty low false trip rate, 1 over 133 years. Now, that sounds pretty good, but, you know, if you have 10 functions, it's 1 every 13 years. If you have 100 functions, it's 1 every 1.3 years. Keep in mind, you really do need a high number to avoid costly false trips. Okay, 100, what's the risk reduction factor? 147. All right. What if we picked more realistic variables? We picked a mission time of 20, so I went to some conservative numbers, a mission time of 25 years. We're going to run the equipment without a major overhaul. We may very well overhaul individual pieces of equipment. I know many valves you refurbish seals and so forth regularly, but it's not a major overhaul, not a rebuild. Proof test interval of 1 year for the sensor and final element, 5 years for the logic solver. Now the proof test coverage is a big deal. 90% for the sensor, it's a pretty good proof test. 70% for the final element. Gee, I may be a little optimistic even if it's a tight shutoff application, but I assumed it wasn't. Proof test duration of 2 hours. Maybe I should have picked 4. Anyway, I picked 2 hours because we're really got to get this. You can't leave it in bypass very long. And an MTTR is more like 48 hours. Maybe that's optimistic. I mean, you can't really tell me people get out there and repair things in 8 hours. I mean, what if it's a holiday? 48 hours, I think, is pretty realistic. But anyway, for example purposes, I chose 48. In maintenance capability, I picked medium for the sensor and final elements, and good for the logic solver because they're relatively simple and relatively foolproof. Now, what's going to happen to this PFDavg? Got a guess? Remember, we were sitting at a risk reduction factor of 147. Now we've made the same exact design, but we're accounting for all 9 of our variables. Wow. Look at that. The calculated PFDavg for this safety instrumented function drops to a risk reduction factor of 17, which barely meets SIL 1. Now, I have done some sensitivity analysis, and all of them have an impact, but I will tell you that the impact of proof test coverage is most significant. The impact of, given our 1 year and our 5 year, the impact of bypass is not that significant in this case. I think it's a big deal. I think it's very important that a competent, responsible, and ethical engineer use and account for all the variables. And there are equations that can be derived. I've given you all the pieces, but I didn't put them all together. Actually, I really should just do that for the latest edition of the book I'm working on. But there's only 20 hours in a day. Look at these variables. Failure rates, detected and undetected. redundancy, proof test intervals, mean time to restore. Those are well known. Those are even covered in 61508 equations, example equations. Proof test effectiveness is even mentioned in the new version of 61508 after it was discovered and commented by Exeter. But mission time, which is part of that, is actually also mentioned in 61508 but not given in the equations. Bypass time, and whether you have to run your proof test in bypass or whether you can run your proof test with the safety function enabled. You know, that's one of the real advantages of some of the partial stroke testing techniques, because often you can run these without bypassing the final element. So there's some real advantages to some of these things that we don't necessarily always think about. And lastly, your operational and maintenance capability. I will tell you that I saw results of field test studies from a chemical plant in Germany, and they indicated terribly effective safety culture and very few site-specific failures. In that case, the product-specific failures generated by an FMEDA matched up very nicely with the actual field failure studies done by the plant. I've seen places where, in fact, the safety culture is not so good. Now, I got another question. Okay. If using an Exeter certified product, the highest proof test coverage assigned by Exeter is the product should be chosen. Exeter does estimate proof test coverage as a function of example proof test methods. And if you are using one or more of those proof test methods, we recommend you use the proof test coverage given by that method. If you come up with a better proof test, you may be able to justify a higher proof test coverage, but be careful. I will admit that several end users have come up with some terribly effective proof tests, and Exeter has estimated the proof test coverages that are better than our FMEDA reports for those specific examples. So proof test coverage is still a big deal. I can assure you, Exeter, we're doing everything we can to give you more and more proof test effectiveness data. And we're publishing more and more average numbers in our new books. We have a new book on final elements and remote actuated valves coming out first quarter of 2015, which will have a whole lot of failure rate and proof test effectiveness data in it. Think about all 9 of these variables. Where do they come from? Well, number one, the failure rates for your product are the responsibility of the manufacturer of that product. They are a measure of the design strength of that product, and the manufacturer is responsible for providing realistic numbers. As you perhaps have seen in our prior web seminars, we do a detailed web seminar on comparing Exeter's FMEDA data with actual field failure data, and found out we're getting a pretty good match. What about variable number 2, redundancy? Does a product manufacturer choose the redundancy that goes into your SIF? No. The system designer chooses that variable. Who picks the proof test intervals? Well, the end user practices establish that, or obviously whomever does the SIF verification calculation can do that. Who establishes mean time to restore? That's clearly a variable established by the end user. It's an attribute based on site practices. Proof test effectiveness. It's absolutely something determined by the proof test method. Now, a manufacturer may give you some example proof test methods, and although some certification bodies don't require that manufacturers give you that, Exida does, at least example conceptual proof tests. But whether they're done or not, or whether you have a better approach, is entirely the responsibility of the owner-operator, the end user. Mission time. Entirely a variable of the end user, along with proof testing, whether online or offline. It's a function of system design at the end user level. Proof test duration is responsibility of the end user, and certainly operational and maintenance capability is a responsibility of the main user. Do you get a picture? Most of the variables in PFDavg are not the responsibility of a manufacturer. Overall, very little is the responsibility of the manufacturer. And so when you see manufacturer's self-declaration, first of all, Exida, we've never accepted a manufacturer's self-declaration without a full safety case to back it up. And whenever we have asked, we were not able to get an assessment report or a safety case. And so most of our customers who want us to verify a system design have to do their own prior use justification, which is absolutely allowed. But one of the things that I'm concerned about is when the manufacturer publishes a PFDavg. Take a look at these numbers down here. What variables were included and what variables were not included? I've searched through this document, and there is no indication of what variables were included or what assumptions were made. This is just not a good situation. One of the reasons it's not good is we had a case where an engineer picked a PFDavg value from a report and used it, then used it to design a safety function which wasn't even close to being sufficiently safe. There was an incident, and actually the engineer blamed it on the PFD number in the report, not doing their own CIF verification. I don't like publishing PFDavg numbers, and I don't like to see them published when they will mislead people into designing poor safety systems. Even some certification bodies publish PFDavg numbers on the certificates. It's very clear to me by looking at this that I look at the number at the top, probability of failure on demand. Then I look at the number on the bottom, average probability of failure on demand. It looks to me like that's a divide by 2. It looks to me, in fact, I double-checked. They're using a simple equation that used nothing but dangerous undetected failure rates, which they call the dangerous failure rate, and the test interval. All the other variables were completely ignored, and this is exactly the kind of a thing that can mislead an unknowing engineer to design a bad safety function. You need to be very careful of this sort of thing. I hope today you've seen that a realistic PFDavg calculation depends on several variables. We've named 9. Some of them are more significant than others depending on the application, but all 9 can be significant. Using simple equations like those in 61508 Part 6 will result in optimistic and unsafe designs, as we've shown you in the example. Equations can be used if all variables are included. Commercial CIF verification tools, several of them are a practical way to include all variables. You need to check to make sure what variables are included in the CIF verification tool you are using. I hope you think this is important and significant. Any more questions? We're hoping this is an important and significant message. And I thank you so much. You've done well. How many users are now looking for the highest proof test coverage to choose their certified products? Gee, I have no idea. But proof test coverage is, in fact, a function of the proof test and not something that is the real responsibility of the manufacturer. And therefore, using proof test coverage to choose a product hardly makes sense. We do have another web seminar coming up on proof test coverage in general, so stay tuned for that. I do think it's quite unrealistic to use proof test coverage as a means of selecting a product. To me, that doesn't make any sense at all. I got some comments. Thank you. We do appreciate the great work. Remember that this web seminar is recorded and will be available online. The slides will be made available to everyone who has registered. And thank you for your attendance. If you have another question that comes into your mind later, please do not hesitate to send me an email. I will answer them asynchronously. There's my email address. And sometimes it may take a while for me to get to you. Oh, I have one more. Thank you, great topic. The comment was, thank you, great topic. I'm ordering your book. Well, I wasn't trying to sell books, but I really want people in this world to be competent. Please get your competency by attending as many of these free web seminars as you can. Read as many books as you can. Meanwhile, thank you very much. Stay tuned for the next Exeter web seminar. Bye-bye.